This is start the afternoon section, the first section of the afternoon. And the first talk is given by Matthew Kleban0 from NYU. Thanks for all the way from Taiwan. And the topic is accidental universe.
First of all, thanks very much to the organizers. I'm really enjoying the conference so far. It's great to be in Taiwan. That's the first time. I should say ni hao. I'm going to describe some work that's been done with Thomas Mackler, who's now a postdoc in San Diego, and with my student Oliver Jansen, who's on the market this year. He's graduated. He's very, very good. And with Kate Eckerly, who's a postdoc in Milan. And actually also applying for jobs this year. So what I'll tell you is in these three papers and in one more, which is nearly complete. It should be out in a couple of weeks. So the title is a play on the title of this book by Paul Davies from the 80s about the entropic principle for reasons that will become clear. All of you are aware of some of these sort of basic mysteries of cosmology. And really sort of the most basic question you can ask about the universe is why it's so large. And then what does that mean, large compared to what? Well, compared to the scale of anything that we know of in fundamental physics. So if you measure the size of the universe, meaning the distance to the horizon, to the cosmological horizon, in units of the Planck length, it's something like 10 to the 60, or in units of the size of a proton, it's 10 to the 40. So how do you get so big? Why is it so big? How do you get this gigantic number out of fundamental physics? And there's another question, which is why it's so old, or a little bit more interestingly, why do we live at the time when dark energy is just beginning to dominate the energy density of the universe? If you went back a couple of factors of 2 in the expansion, dark energy would be a tiny fraction of the energy density, and if you were to go forward a couple of factors of 2 in the size of the universe, it would be nearly 100% of it. So why do we live at this special time? This is called the why now problem. And why is the universe so smooth and so isotropic that fluctuations in density on large scales are only a few parts in 100,000? And the energy density seems to be almost exactly the critical density given the expansion rate. In other words, the geometry of the universe seems to be almost exactly flat. So why is that? Now, these questions are tied up in the cosmological constant problem, the problem of why the vacuum energy is so much smaller than the scale given by particle physics. Because if the cosmological constant took its natural value, then the universe would be tiny, the distance to the horizon would be some particle physics scale. And so if you want to explain these problems of why it's so big, you have to solve the cosmological constant problem. And of course that's tied up also in this age question. Dark energy would have dominated almost immediately in the very early universe if it was large. Smoothness, isotropy, and flatness, that can all be explained by a period of inflation in the early universe. But why was there a period of inflation in the early universe? So inflation seems to require, it's not very natural. It takes some degree of tuning, either in the potential or maybe in the initial conditions. So, why did that happen? Why was it necessary? So here's just sort of an executive summary of the expansion history of the universe and the standard model of cosmology. There was some event at around 14 billion years in the past, the Big Bang. And we believe that was followed by this period of slow world inflation. We don't know much about inflation, but we do know that it must have lasted at least roughly 60 e-folds. An e-fold is increasing the linear size of the universe by a factor of e, 2.71. It must have lasted at least this long, otherwise it wouldn't explain flatness and so forth. After inflation, there was a period of radiation domination, around an expansion factor of 3,000 or so in the past. Matter took over from radiation as the dominant energy component. And most of matter seems to be cold dark matter, not baryonic matter. And a factor of a couple in expansion in the past, dark energy took over with this incredibly tiny energy density. So the simplest explanation, we don't know exactly what dark energy is, but the simplest explanation for it is that it's a vacuum energy. It's an energy of empty space. That fits all the observations. And the constraints on the equation of state of dark energy are getting better and better, and really zeroing in on this. But if dark energy is a vacuum energy, actually no matter what it is, but in particular if it's a vacuum energy, then to explain this tiny value in a world governed by laws of physics where the scales are all so much larger, it seems to require that the dark energy density not be a unique, there not be one value of dark energy of the cosmological constant, but rather some kind of large number of phases. In different phases, vacuum energy takes different values. So if you have a large enough number of phases, then you have a large number of different possible values of vacuum energy. So there's not one unique value, there's many possible values. And if there's enough of them, then there's going to be some phases which have vacuum energy consistent with what we observe. Of course, then you can ask, why do we live in a special one that has this tiny value of dark energy? And for this, you need a little bit of the entropic principle. This was proposed long ago by Steven Weinberg and others. The idea is that in a phase where the vacuum energy takes its typical value, very high, there's no structure, there's no life, there's just nothing going on there. And so asking why we see a small value of the vacuum energy is like asking why we live on the surface of a rocky planet, which is an extremely special environment in the universe. Most of the universe is empty intergalactic space. Why don't we live out there? I think I once calculated the volume of the universe that's close to the surface of a rocky planet divided by the volume of the total universe, and it's about 10 to the minus 40. But no one worries about that, because it's obvious why we live on the surface of a rocky planet. There's no one in intergalactic space. So that's the kind of explanation that was proposed for the smallness of the CC, of the cosmological constant. But the requirement for that, if the fundamental scale of the theory is the Planck scale, is that the number of different phases should be larger than the inverse of this value in Planck units, which is something like 10 to the 120. So you need a theory with an enormous number of phases. Sometimes these are called vacua, metastable phases, with differing vacuum energy. So here's a picture of the kind of potential energy function that you would need. And you can see these are just the values of the energy in the minimum plotted over here. If you had enough of these, eventually this will get filled into a kind of discretuum, and there will be some phases with very small vacuum energy. Okay, so this is an interesting argument. Let's dig into it a little bit. So this argument that was made by Steven Weinberg, where he predicted the value of lambda, was that if lambda were larger, then given what we know about our universe, so holding everything else fixed, if you were to make the vacuum energy larger, structure would become exponentially rare. There'd be very few galaxies or stars. The reason for that is that perturbations in density only grow during matter domination. They don't grow during radiation domination. They don't grow during lambda domination. They wouldn't grow during curvature domination if you had a period of that. And so, in order for perturbations to grow to become order 1, where nonlinearities take over and stars can light up and galaxies can form, you need to have a long enough period of matter domination. Otherwise, you'll never have any stars. And so you have to have lambda, which doesn't dominate until after matter does. Okay, so this is true. But it's having small lambda is not sufficient. So, for instance, here's a reason why it's not sufficient. So imagine you have a theory that has all of these metastable phases. So how do you get into them? How do you populate them? And the answer is you populate them by tunneling. So these are just metastable phases, and there's first-order phase transitions that connects them. So if there's a part of the universe that's in some typical phase with very large vacuum energy that I've labeled TD for true vacuum, or sorry, FV for false vacuum, a region of a lower energy vacuum, of the true vacuum, can form, a bubble can form, by tunneling. And it turns out that inside one of those bubbles is a complete Friedmann-Robinson-Walker cosmology, which we might live in. But it's an FRW cosmology that has open curvature. And it turns out that open curvature, that's like faster than escape velocity expansion. It means for a given energy density, the universe is expanding faster than the critical speed. So that's faster than escape velocity expansion, and that faster expansion inhibits structures from forming, just like positive lambda does. And so if you want to have structures in a universe that form this way, you've got to get rid of the curvature. You've got to inflate. How much do you have to inflate? Well, you need roughly 60 folds of inflation after the bubble forms to get rid of the curvature. Otherwise, curvature would dominate before matter does. And again, prevent structures from forming. So small lambda is necessary, but it's not sufficient. And actually, it's not even really necessary, because in this argument that Weinberg made, he held everything else fixed and then varied lambda. But if you could vary some of the other parameters of the universe, you could make structure form even with much larger lambda. For example, if you had large fluctuations in density, not a few parts in 100,000, but much larger, then structures are going to form no matter what lambda is. Black holes will form by collapse, for example. Gravity will become nonlinear and strong. Furthermore, if you had a larger ratio of matter to radiation in the early universe, then matter domination would have happened earlier than it did in our universe. It would have happened at a higher energy density. And since the constraint really is that dark energy shouldn't dominate until after matter does, if matter dominates earlier at a higher energy density, then dark energy could have been larger as well. So all of these considerations undermine this argument, this entropic argument. And if you really wanted to test this argument and see whether it holds water, you should study all the possible cosmologies. You should look at all of the universes which occur in your theory. And then you should maybe restrict your attention to the ones where structure forms, so we could possibly be living there. And then within that set, you should ask, what are the typical values of the CC? What kind of spatial curvatures do those have, et cetera? And does that agree with what we observe? Is what we observe typical, or is it very unusual? But another problem with that is that if you have a theory that has this number of metastable phases, 10 to the 120, then it's terribly complex. Any theory that has that many phases, it must be very complicated. And it's even been argued, incorrectly, but it's even been argued that finding any minimum in a theory with that many phases is computationally intractable. That even if I were to hand you a theory, you wouldn't be able to ever find phases that had dark energy in this range. This is what I was calling the lambda, sorry. Just because there's so many that it would be hard to locate them. And if you can't even find minima, then good luck trying to study cosmology, which is a dynamical process with a Big Bang and so forth and so on. So what I'm going to do in this talk is I'm going to describe to you a theory of axions, multiple axions, which is a landscape theory like this. It has many metastable phases, many metastable minima with a huge range of values of the vacuum energy. In this theory, there's some dimensionful parameters, which can all be taken to be at the gut scale or the string scale, just an order of magnitude or so below the Planck scale. So a very high scale theory. There's some dimensionless parameters, which can be taken to be order 1. And in fact, all these things can be chosen randomly from random distributions, if you want. It's really not very sensitive to how you pick the parameters. Nevertheless, it's tractable. So on this laptop, I can generate an instance of a theory like this, and I can find 10 to the hundreds of minima. This number will depend on the parameters. I'll describe that in a moment. But I can find this order of minima in a few minutes. And when I say find, I mean I can locate them in field space, and I can study their characteristics in detail. And it's going to turn out that in this theory, if you look at cosmologies which eventually form structure, by which I simply mean there's some dark matter, there's some perturbations in it, and I just want those perturbations to grow to become order 1, sometime, somewhere. If I just select out the cosmological histories with that property, they look a lot like the universe we live in. Despite the fact that there's no or very little model building in here, I'm not choosing any parameters carefully, and everything is up in the gut scale. So this really provides an example of how one can answer the questions that I started with. Maybe it's not the right answer, but at least it's an answer. And like I said, the scales in this theory will be at the gut scale, but in the end I'm going to talk about ultralight or fuzzy axions, which also emerge naturally here. All right, so why would you think about theories with multiple axions? Well, one motivation is string theory. String theory has lots of moduli, and it tends to have hundreds of axions in a typical compactification. So that's one motivation. What characterizes axions, apart from being pseudoscalars, is that they have some exact shift symmetries. And they have a potential which is periodic under those shift symmetries. So it's generally of the form of the sum of of cosines. It's not particularly crucial for this that the functions be cosines, but let's take them to be cosines. And inside each cosine, the argument of each cosine is some linear combination of the axion fields with, let's say, integer coefficients. It could be rational, but that won't matter either, so let's make them integer coefficients. So the theory is basically a sum of cosines of just linear combinations of the axion fields. And to define my terms, I'm going to have capital N axion fields and capital P, so capital P of these cosines. The 1 here is just picked for convenience, so this part of the potential is not negative, and then there's a constant. There's also, I could choose the kinetic term here to be general, as long as it's positive, so there's no ghosts. Now, this theory is only interesting, well, actually it's interesting, people have studied it in lots of different regimes. But if I were to choose P to be less than or equal to N, then you can diagonalize the arguments of these cosines. You can just rotate in field space, and you just have a sum of cosines, cosine of phi 1 plus cosine of phi 2, and so forth. And in that case, there's only one minimum that's unique. You can, of course, shift by these shift symmetries and get to other minima, but there's only one vacuum energy in that theory. On the other hand, as soon as P is bigger than N, you can't diagonalize anymore because you would have to solve P equations in N variables. So as soon as P is bigger than N, you can no longer diagonalize. And it turns out that you go from having one minimum. Well, let me give an example just to show you what this looks like first, and I'll tell you what happens. So here's an example with P equals 3 and N equals 2. And you can see there's some exact shifts here. So for example, this is the same as this. Okay, so there's some exact shift there. And there's also some kind of approximate shifts as you go, for example, along here. Things aren't changing very fast. They're changing, but not very fast. So there's both exact shifts from here to here, and some kind of approximate shifts from here to here. As I mentioned, there's going to be, if there are n axions, there's going to be n of these exact shifts, n exact periodicities. The theory is defined on an n torus, or a rank n lattice. And so you should just focus on one fundamental cell of that lattice, otherwise you're just repeating yourself. And then you can see in that picture that there are some additional approximate shift symmetries. In general, there's p minus n of them. This actually turns out to mean that you can ignore the phases that I had in there originally. Okay, so now how many minima are there? So if p is equal to n, or p is less than n, there's one minimum. One value of vacuum energy, one unique minimum. If p is greater than n, there's something like the square root of p factorial minima. So for example, if p is around 100, then there's about 10 to the 100 minima. The reason this happens, well, I'll describe in a moment why it happens. But one way to see why it happens is pretend that you had more axion fields. So pretend you had p instead of n. Then you can diagonalize this potential. And then the potential is just a sum of cosines. But to go back to the original theory, you have to constrain that function to a linear subspace, an n-dimensional subspace of this p-dimensional space. And you can do this with Lagrange multipliers. This is why Lagrange invented Lagrange multipliers in the first place, actually, was to constrain functions of higher dimensions to subspaces. So you can do this with some Lagrange multipliers. Here's a picture of it. So again, this is p equals 3 and n equals 2. So you have a simple potential in this three-dimensional auxiliary space. And then you slice through it with some plane that's at some angle. And that simple potential evaluated on that plane is the physical potential. And it turns out that the cosines of the angles, if you were to choose all these parameters randomly, or any way other than very carefully, you'll find that the angles are such that that surface travels very far before it intersects another lattice. If it's at a lattice point, you have to travel very far before you intersect another one. And this has to do with the fact that if you think of this matrix as if you think of these coefficients here as a p by n matrix, you can't take its determinant because it's rectangular. But you can take the product of its singular values. Take the determinant of q transpose q. That's a square matrix. And determinants are generally very big. Determinants scale factorially with the size of the matrix. That large number turns out to determine the denominators of the cosines of the angles of that linear subspace that I showed you before. So the cosines of the angles will be rational numbers, otherwise you wouldn't have any periodicities. But the fact that these are integers guarantees that the cosines of the angles that determine the angle of that thing are rational numbers, but their denominators are very big. So this gives rise to these approximate shift symmetries that I mentioned. So here's a bit of a contrived figure, because this is now p equals 2 and n equals 1. But you can see here's an exact symmetry, like that. And here's the approximate symmetry. You go from here to here to here to here, and so forth. And you only change the energy in the vacuum by a little bit. Okay, so this is the reason why these theories are tractable and why they have a discrete realm of vacuum energies. Just one more picture to convince you this is working. This is with p equals 40 and n equals 23. I had to exaggerate this to make it visible at all, but here's an exact symmetry direction, here's an approximate symmetry direction, and here's just a random direction in the field space. And here's an output of the algorithm I was telling you about. So this tells you that there's a minimum at this crazy looking rational number, which is here, and you can see, well, you can't be sure it's a minimum because it's just a plot all in one direction, but it is. You can see it. There's a spike down there that this lines up with. So these techniques work. They're very efficient. These coefficients here, again, thought of as a matrix, can be pretty sparse. It can have a lot of zeros in it. As long as it's not so sparse that it'll have entire rows of zeros or columns of zeros. That's fine. Or it doesn't have to be sparse. It can be dense. And here's a more sophisticated formula for the number of vacua. But roughly speaking, it goes like the square root of p factorial. So again, here's another example. If I choose these coefficients to be plus 1, minus 1, or 0 with equal probability, then I choose p to be 501 and n to be 500, I get 10 to the 500 vacua. 10 to the 500 is kind of the number that got thrown around a lot. That's why I picked these numbers. Okay, so you have all these vacua. They all have different vacuum energies. And there's a smooth distribution of vacuum energies. There's nothing special about 0. So you'll have plenty of vacua with vacuum energies in the range we can see. Thanks. Now these are metastable vacua. They can decay. Decays are exponentially suppressed, so it's possible for them to be very long-lived. And if you work out what's in the exponent, it's something like this. And this can easily be bigger than 1,000 or more, which is enough to guarantee that these vacua are stable on billion-year timescales. Okay, so you have at least a landscape theory that provides many different values of the vacuum energy, so it satisfies that criterion. But now I want to study cosmological histories in this landscape. And I mentioned that if you're going to populate these different minima by tunneling, then you have to have inflation afterwards. And I mentioned also that inflation requires some kind of tuning, at least one would normally say. For example, the derivatives of the potential measured in Planck units have to be small for inflation to happen. And if you take a theory like this, so now we need to know about the kinetic term. Let's take the kinetic term just to be 1 over f squared. So the identity matrix with f being the scale, and f being, like everything else, 10 to the minus 2 m Planck. Then v prime over v in Planck units, that's m Planck over f squared. That's a big number. It's much larger than 1. So how are you going to have inflation? It doesn't look like it's even possible. Except that you've got many directions in field space. And when you have many directions in field space, some of them are going to be flatter than others. For example, even if you're in a two-dimensional field space, the lattice is some kind of parallelogram or square, and the diagonal of the square is longer than either side. This was the idea of inflation. And there have been many ideas since inflation that are sort of riffs on that theme. They're called kinetic alignment or clockwork inflation, K and P. So the analysis that I'm doing here, it actually takes into account all of these. It generalizes all of these analyses because it takes the most general potential of this form you can write down. And what you find is that the typical distance in field space, which you would have thought of as f, because that's the periodicity of this cosine. If you canonically normalize the field, then this becomes 1 over f, pi over f. So f would have been the periodicity, or 2 pi f would have been the periodicity of this potential. Instead, there's an n to the 3 halves. And, well, in view of the time, I won't explain exactly where this comes from, but it's there. So if n is 100, that's a factor of 1,000. So it's easy to get field ranges that are much larger than the typical scale of this potential by a factor of this n to the 3 halves. And so this can allow for slow roll inflation. If you just randomly sample the field space, so another interesting thing about this theory is that you could treat it as an inflationary potential. You could ask what kind of predictions do you get for inflation. Well, if you just randomly sample the field space, this is n sub s, the scalar tilt. This is r, the tensor to scalar ratio. You basically tile this plane, including some very small r's, and some very large R's, a whole range of N sub S's. By the way, the observational constraints are sort of here. There's lots of different types of inflation. They have lots of different features. There's turns in field space and so on. I haven't investigated this in detail, but it would be interesting to do so. But if you look at the kind of inflation that happens after tunneling, then it's actually rather predictive. There's only really one sort of inflation that takes place. Well, first of all, you might say, well, how can you have inflation after tunneling at all? People did say this in the 90s. Tunneling requires large second derivative in units of d. And slow roll inflation requires small second derivative. So it sounds like, how can you have them both? Well, again, when you have multiple directions in field space, you tend to tunnel through the thinnest barrier, which has the largest second derivative. It's a thin thing, so it's got a large second derivative. And then you find yourself displaced from the minimum you're going to end up in along other directions, including those that have small derivatives. So you sort of roll down the steep directions first, then you roll down the shallow directions and inflate. So there's no tension at all, actually, between tunneling and inflation when you have lots of field sections. And you can ask, what's the typical number of e-folds of inflation? After tunneling, it depends on the parameters, but it has a power law tail. So even if you're in a situation where you usually don't inflate much after tunneling, it's not very suppressed. It's not very unlikely that sometimes you will inflate quite a bit. Furthermore, these inflationary trajectories take place going down into a minimum where the potential is not very far from quadratic. And so all those trajectories have almost exactly the same delta rho over rho. And so this helps deal with the problem I mentioned before, that if delta rho over rho was much bigger, the entropy constraint on lambda would be much less constraining. Instead, all of these inflationary trajectories have more or less the same delta rho over rho, which with these numbers works out to be roughly right. It's 10 to the minus 4 or a few times 10 to the minus 5. All right, what about dark matter? If you want to explain our universe, you better have some matter in it. Well, imagine that this rectangular matrix up here is not full rank, which means just that there's some linear combination of these axions which doesn't appear in any of these cosines, which doesn't get a potential. There's something called the weak gravity conjecture, which extended to axions tells you that there should be no exactly massless directions. There should be no exact continuous shift symmetries in quantum gravity. And it's believed that in a theory which does have such a symmetry, gravitational instantons will generate a potential, which will again be a cosine, but with a scale which is m Planck to the fourth times e to the minus s, and this s will be of order 1 over f. So of order a few hundred, e to the minus a few hundred. So that's a huge suppression. And there's something which I like to call the fuzzy miracle, because it's a little bit like the WIMP miracle, that with these scalings, it's easy, well, it's plausible, let's say, to get the energy density of dark matter that we see today. The energy density of dark matter is exponentially suppressed. It goes like e to the minus 1 over f. So here's a formula for omega today in these units. And so plugging in these numbers I've been using gives you, or it could give you, without having to choose an unnatural value for any of these parameters, the right value of the dark matter energy density. And since the entropic constraint is that lambda should dominate after matter, this gives you a formula for the cosmological constant. It's e to the minus a few divided by f in Planck units. So there's an explanation, if you want, directly from here, for why the cosmological constant is so small. There's a formula for it. It's exponentially suppressed in f, where f is about 10 to the minus 2. It's about the string scale or the Getz scale. Let me skip this because we're out of time. You can still solve the Stark CP problem here. It doesn't change anything. Just to summarize what I said, if you take a theory of a few hundred axions with random couplings and all the dimensional scales, all the energy scales up near the Getz scale, and then you ask, what are the cosmological histories in this theory which form structure ever, at any time? And what do they look like? Well, they have a tunneling event, which is the Big Bang. They have at least 60 folds of inflation, not too much more, but roughly 60 folds of inflation. They have a period of radiation domination. If you couple these axions to QCD or to any kind of U1, you overheat to radiation. They have a tiny amount of dark matter, which will dominate when the universe is very old, and an even tinier amount of dark energy, which will dominate just after that. So you get a universe where dark energy dominates not long after matter does, and where both matter and dark energy at that time have an energy density that's suppressed exponentially from the Planck scale, e to the minus a few times m Planck over f. In other words, oh, and I should say, since 60 equals inflation, they'll be nearly flat, and they'll have primordial perturbations, which are nearly Gaussian, have the right amplitude. I should have said that as well. Right. So pretty much all the gross features of our universe pop out of this without model building, with random parameters. Okay, so I'll just say there's a lot of open questions. So one of them, there's this weak gravity conjecture. There's other conjectures in the same class, one of which is that there aren't any de Sitter minima in any consistent theory of quantum gravity. If that's true, we're in trouble for a lot of reasons. If it's not true, as I rather suspect it's not, then you would want to know if you're going to, if you believe in string theory or any kind of quantum gravity, what sort of axion landscapes do you actually get? So here I'm choosing everything randomly, but surely it's not random. So what is it really? What is this matrix? What are these kinetic matrices? What about couplings to all the other moduli? That's a big problem. And this was just the first model. As far as I know, this is the only model which has enough minima that you can actually solve the CC problem this way, and which gives any kind of reasonable cosmology with it, even allows you to study this question of what the cosmology looks like. And it works extraordinarily well, much better than I was expecting it to. So was that a coincidence, or is that a generic feature of theories with many metastable phases? Okay, so I'll stop there. Take any questions.
If I impose the recently talk about the swarming criteria, will this model survive or consistent?
Not if you pose all of them, that's for sure. Right, so that's what I was referring to. But yeah, so it's consistent with weak gravity. In fact, it needs weak gravity in some sense, but not with Swampland distance conjecture, and not with the non-existence of inflation or de Sitter minima, of course. But I must say, I don't think those conjectures are very well motivated. I'm happy to talk more about it.
Short question.
So in your model, you have a small CC. That is because the tunneling effect eventually go to the lowest minimum.
The lowest minima in this model would be negative.
Yeah.
So if you tunnel one of those, you crunch. And if you tunnel to a typical one, which has a very large negative CC, you'll crunch in a tiny fraction of a second. So the universe just ends. The ones that have small CC are the ones that just by coincidence happen to be close to zero. So in this model, there's what's called a discretuum, sometimes almost a continuum, but it's a discrete set of different values of the vacuum energy from minus, m gat to the fourth to plus m gat to the fourth. And as long as the spacing is fine enough, there's a few that are close to zero. Those are the only ones where structure can form.
I have about the first miracle, any physics origin of this miracle, or just purely by accident?
You mean where does this formula for the abundance come from, or why does it work out like that?
Yeah.
Yeah, I mean, I think it's interesting. It's not what you would have expected necessarily. I really do think it's sort of logically at the same level as the Wood miracle. There's kind of one number that comes out right, given natural values for the others. Yeah, and it's testable if the mass is in around this range. If the mass is a bit heavier than that, it becomes harder. But it's a different kind of dark matter. The de Broglie wavelength is huge. If it's in that range, the de Broglie wavelength is kiloparsec almost. If it's a little heavier, it gets smaller. But still, it's not at all particle. Well, it's a particle, but it's a particle with a huge de Broglie wavelength. So it's a testable thing in principle. All web searches will fail for one thing. That's true.
Okay, we should stop here. Okay, thank you, Mike.